afternoon or good morning, whenever you are watching this. We are doing chapter 10, part 4, the last part, thank God. Okay, so last time we talked about standing waves in a string, right? First, we started off with an equation. Let's use purple for this. So we started with, okay, V equals to F lambda. We've seen this equation in chapter 9. And the V in a string is also equal to tension over mu. Mu is the mass over length, right? So if I were to rearrange the first one to find the frequency, I would get V over lambda, and substituting V as this guy, it gives me 1 over lambda T over mu. And depending on what lambda was, we substituted lambda in terms of L. So we had a series for F1, a series of harmonic. We had 2L for F1, square root T over mu. And then we had for F2, the second harmonic was 2. Okay, sekejap. And we had 2 over 2L T over mu, and for the third harmonic we had 3 over 2L square root T over mu. And with this pattern we concluded, okay, so we can generalize this series of harmonics into an F1 n equals to n over 2L, right? Because it's a multiplication of the fundamental frequency. So 1 over 2L, so times with n T over mu, square root that. Okay, sorry for that, berterabur sikit. So that is for the string. Now we are talking about standing waves in air columns. This was for string. Okay, what was the equation? This guy. What was the point that I asked you to remember? For a string, the node must be at the end. Nodes must be at the end, because the ends of a string are fixed. We have to hold it, or it has to be attached to something for us to vibrate it, right? So the ends are fixed. When the ends are fixed, you have a node. Fixed, you get a node, okay? So now let's talk about standing waves in air columns. If one end of the air column is closed, so you get n because that part is fixed, right? A node must exist at this. And since the movement of air is restricted, okay, so you just have to say, okay, if something is fixed, if something is closed, or if something is attached to a wall, if something has like something holding on to it, it means that it is fixed, the movement of air is restricted. You start with the node at that point, okay? However, if the end is open, the elements of the air have more freedom, right? So you get an antinode. The wave can oscillate from the maximum to the minimum. So that's an antinode for you. Alright, so let's take a look. So this is an example of tube that is open at both ends. So both open. Kalau open, flexibility or freedom, which means that your ends start with antinodes. So this guy is antinode, node, antinode. Of course, lepas antinode, we always have to follow with node, we always have to follow with antinode and then node. It's repetitive, right? And again, A and A and A over here, A over here. Okay, so depending on how many loops that you have, your length is, you have to write your length in terms of lambda. So we know that for a complete lambda, it should look like this. Right? This is 1 lambda. Okay, we already talked about this. For 1 lambda, it should look like this, which means that half a lambda will have this guy, 1 over 2, and half of this will be 1 over 4. Okay, so this is 1 over 4, this is 1 over 4, this is 1 over 4, and this is 1 over 4. Okay, so if I were to label my nodes and antinodes, okay, let me rewrite this to be nicer. Okay, so I've rewritten, I've redrawn the wavelength. So this is one wavelength, right? This whole thing is one wavelength, and 1 over 4 is this much. 1 over 4, 1 over 4, 1 over 4 equals to 1 wavelength, right? And if I were to label the node and antinode, so I have NA, NA, and right? So node is where the displacement is 0, antinode is where they can fluctuate from the maximum to the minimum. Node is when it's 0 again, so you have NA and AN, right? So 1 over 4 of a wavelength is NA or AN, right? Okay, so here, let's take a look at this diagram. So here we have AN, A. So I can say this is 1 over 4 and 1 over 4, which is equal to 1 over 2, right? So this is half a wavelength. Let's use a different color. I'm having trouble drawing today. So let's use blue. Okay, so this is 1 over 4 because this is N and this is A. This is A. This is also 1 over 4. This length gives me 1 over 2 lambda. How about this length? We have A, N, A, and A. So this is 1 over 4. This is 1 over 4. 1 over 4, and this is 1 over 4. So 4 of 1 over 4 gives me 1 lambda. So that is 1 lambda. My L is 1 lambda. And about this guy, this is A, N, A, N, A, N, A. So this is 1 over 4, 1 over 4, 1 over 4. Ito da. Okay, it's here. This is 1 over 4. Saya juga akan besarkan. 1 over 4. And this guy is 1 over 4. So I have 1, 2, 3, 4, 5. Terlebih ni. A and A and A and A. So 1, 2, 3, 4, 5, 6. Oh, betul lah. So I get 6 times 1 over 4 is 3 over 2. So that is 3 over 2 lambda. Okay, so now that we know how to calculate your lambda, which is NA is equal to 1 over 4 or AN is equal to 1 over 4 of a lambda, let's look at the equation. So here they said, okay, so L equals to 1 over 2, which is correct. We found out that way as well. And L is 2 over 2, which is just 1. Betul. And then L is 3 over 2. Betul juga. Okay, so rearranging, we had an equation before. Kenapa rasa macam tak cukup tempat nak tulis ni? So previously we had this equation, F equals to V over lambda, right? And we substituted lambda in terms of L. So here our L is 1 over 2 lambda 1. So F1 is, so rearranging this, I will get 2L equals 2 lambda. Okay, so this is 2L. And rearranging this, I will get 2 over 2. 2 over 2L is equal to lambda. So 2 over 2L. Third. And then this guy becomes 2 over 3L equals to lambda. And of course, sama juga. You get your mana tadi? Kenapa tak tulis kat sini? It's 3. 3 over 2L times V. Okay, sama. Okay, so the point that I want to make for this particular slide is you should be able to calculate the wavelength in a particular air column. So start with your NAN, start with your labeling your nodes and your antinodes, and then decide for each AN or each NA that is a quarter of a wavelength, and then sum up the number of wavelength that you get. So your L equals to something wavelength. Then you can substitute into your equation. Okay? So yang ni untuk tube open at both ends. What about a tube that is closed at one end? Okay, sama juga, we start with labeling our an. So this guy is closed. This part of the tube, this part of the air column is closed. Maksudnya ada penghadang. I don't know how. Maybe ada wall. Maybe they put a plasticine. Who cares? But it's closed. So when it's closed, the movement of air is restricted. You should start with node. Node, node. Okay? So here they said AN. So this means that we have 1/4 because we only have AN, right? It's either NA or AN gives you 1/4 of a wavelength. We have discussed this in the earlier slide. So this guy is ANA. Okay, so this is 1/4, 1/4, 1/4. So that is 3/4. This is 1/4. This is the sum. Okay, so this is 1/4, 1/4, 1/4, 1/4. You get 3/4s. This guy is 1/4, 1/4, 1/4, 1, 2, 3, 4, 5. So you have 5 1/4s. Okay, so this gives you a sum of 5/4. In terms of the fundamental frequency, right? So the fundamental frequency is, so here, your L is equal to 1/4 of a lambda. Your L is 3/4 of a lambda. Your L is 5/4 of a lambda. So if you were to substitute your lambda in terms of L, the same thing that you should do just like before. So your F is equal to, this is F1, this is your fundamental frequency. It is, lambda, sorry, it's V over lambda, right? So V over lambda, and lambda is 4L. So that is your fundamental frequency. So this is, we don't know yet what N this is. So V over 4L, but this guy is 4/3. Kejap. This is 4/3L. And this guy, we don't know as well. This guy is 5/4L. So in terms of the fundamental frequency, we can say that this is 3 times F1. And this guy is 5 times of F1. Which means that this is our 3rd harmonic. And this is our 5th harmonic. This is our fundamental. Okay, tadi we had 1, 2, 3. Now, for a tube closed at one end, we have 1, 3, 5. Okay, remember, NA or AN gives you half a wavelength. That is how you calculate what harmonic it is at. Okay, so this is a diagram showing you if both of the ends are closed, closed. Oh, ada tulis kat situ. So this is for closed. The air column is closed at both ends. Ada dua-dua ada plasticine, or dua-dua ada kertas, or dua-dua ada wall. This is when it's open. So you start with A and A. This guy, you start with N and N. This guy, this is open, closed. So A over there, N over there. So the N part is the closed part. This is open, right? So here they show you the L is 1/2, 2/2, 3/2. We discussed this earlier. This sama macam string. Similar to string. Sebab string pun closed at both ends, right? The movement of air is fixed at both ends. So this is why a closed air column has a similar orang cakap pattern to a tube. Similar pattern to a tube. Similar pattern to a string. To string. Okay, but this is an air column that is fixed at both ends. This guy is open, and as I mentioned before, you start with A, you end with A. And for an open closed air column, you start with A and with N at the fixed point. So here we can summarize how our general equation for these situations. Okay, so harmonic for close, close, and open, open, we have the regular one, 1, 2, 3. And we know that the equation is similar to the string. So that is n over 2lv. Okay, so that is for the fundamental frequency. Do not fundamental frequency just. So f1 equals to 1 over 2lv. f2 is 1 over 2lv. Silap, 1 over 2 over 2. f3 is 3 over 2 lv. So the general equation is n f1 n over 2l, okay, because your fundamental frequency times with an l, v. So what is your v here? So for the v for a string was t over mu, because we had tension and we also had to account for the mass over length. But for an air column, we already know how to calculate for the speed of sound in air at room temperature. So it's just a constant. So it's 343 meter per second. You don't have to use the equation t over mu, but instead use this value because it's a constant. So this is for air column. Okay, this is air column and this is for string. So open sama juga formula dia. Instead of node, it's antinode and antinode, but the harmonics equation is similar. Okay, sama juga. It's 2 over 2 lv. f3 is 3 over 2 lv. So general equation becomes nf1 equals to n over 2 lv. Let me check, betul tak? Okay, betul. This is it. Okay, so the harmonic for harmonic for open close air column. So we know that the harmonic goes from 1, 3, 5, right? Because it's a weird situation. So f1 is 1 over 4l. Tadi 2 Tadi it was 2l. Now it's 4l times with v. The v is also the same as this guy, 343, constant. In air, the speed is constant, the speed of sound. And then we have frequency number 3, which is 3 over 4lv. And then for 5, let me make this smaller. So that is 5 over 4lv. General equation is nf1 n over 4l times with v, where v is your 343 meter per second. Okay, so that is your standing wave in air column. Perbezaan dia, open, antinode, close, node, open, close, antinode, node. Okay, when the movement of air is fixed, you have a node. AN or NA gives you a quarter, 1 over 4 of a wavelength. So that's your summary for that part of the chapter. Moving on, let's do our problem example. So the range of a certain pipe organ is from 8 Hz to 30 Hz. So the range, so this is the range of frequency, is from 8 to 30,000 Hz. What range of pipe lengths? Tanya, what is the range of pipe lengths? Maksudnya, your length is not fixed. If they are open at both ends and closed at one end. Okay, so remember, what is the equation for open at both ends? Assume that the speed of sound is 343 meter per second and the pipes all resonate at their fundamental frequency. So no matter the length, right? These guys resonate at the fundamental frequency. So we need to find the range of pipe lengths. We need to find delta L. Okay, so what is the equation for open at both ends? So open equation is NF1 N over 2L V. Can? But they said assume that all pipes resonate at fundamental. So we are just concerned with N equals to 1. So when N equals to 1, this equation becomes F1 1 over 2L 3, 4, 3. Now I have to find the range for L. So I plug in 8 first. So 8, 1 over 2L 3, 4, 3 equals to, and then I plug in the maximum hertz, maximum frequency, which is 30,000, equals to 1 over 2L 3, 4, 3. Now I solve for L. So L1, L2. So L1 should give me berapa? Use my calculator kejap. So L, if the frequency is 8, it is 21.4 meters. Okay, and if it's 30 hertz, the L should be 0.00572 meters. So delta L goes from 0.00572 to 21.4 meter if the range of frequency is from 8 to 30 kilohertz. So that is your first answer, your A. E2 2. 0.057 to 21.4. Maksudnya length dia berubah-ubah. It gives you a different frequency. Okay, but they all resonate at the fundamental frequency. Okay, so B. What is the equation if it is closed at one end? So maksudnya open, close, right? What is the equation for an open, closed situation? Open, close. Sorry, hari ni macam banyak distraction, so I'm not really focused. So open, close, the equation is N. So this is N over 4L. Kan, tadi 2. Now it's 4 because it's open, close. I told you open, close is the only weird one. Times with V. So everyone resonates at the fundamental frequency. So N equals to 1. And it goes from 8 to 30 kHz. So that is 1 over 4L. 3, 4, 3 gives me L1. And then 30,000. 1 over 4L. 3, 4, 3 gives me the second L. I mean the range lah. And then solving for that, L1 should be equal to 10.72 meter. And L2 is 2.86 times 10 to the minus 3 meter. So the range of L should be from 2.86 times 10 to the minus 3 to 10.72 meters if the range of frequency is from 8 to 30 kilohertz for an open-closed air column. Okay, so that is your example. So let's do the second one. Okay, so here let's read the question first. A closed organ pipe. Closed, right? Closed, maksudnya it's closed on both ends. Organ pipe is 3 meters long. So let's write that down first. 3L equals to 3 meter. The situation is close, close. Which should also, the equation is similar to open, open, right? So the equation should be NF1, N over 2L, V. At what frequencies between 20 Hz and 20 kilohertz will this pipe resonate? Okay, so it's asking at what frequencies will they resonate? And we know that we have harmonics, right? So let's first find the fundamental frequency. Dia cakap kat sini, don't try to calculate all 350 frequencies. Find the first few and then try to find a general formula for the others. We already know the general equation. So let's find the fundamental frequency first. So F1 is 1 over 2. L, we know that it is 3. V is 343. It's a constant. So your fundamental frequency is, not done this one yet. Gonna buat jap. divided by 3 divided by 2. So that gives you 57.17 hertz. Okay, so your other harmonics is Fn and F1, or n times 57.17. Now we have to figure out what is the value of n that overlaps with 20 to 20,000 hertz. Okay, so what we do is 20 divided by 57.17. 20 hertz divided by 57.17 gives me 0.34. Tak apa, kita buat dulu. So 20 divided by 57.17 gives me 0.35. Remember, n is always an integer. So maksudnya dia tak overlap lah kat sini. Betul tak? So the first overlap happens at 57.17 lah, obviously, because that's the fundamental frequency. So it happens at n equals to 1, 57.17. So, nak ambil bateri, sekejap. Okay, I'm back. Commercial break over. Okay, so n is always an integer, So you can't have like 0.3, 0.5, no. You have to have a whole number, which means that n should always be 1, 2, 3, 4, 5. You know what that is. Okay, so I'm not teaching you maths here. So n should always be an integer. Okay, so that means that the first overlap happens at 57.17. So that is n equal to 1. Okay, great. Kita dah tahu yang tu. So let me just rub this off. So n equals to 1, we know that happens. Where, at what n do we reach around 20,000 hertz, right? So 20,000 hertz divided by 57.17 will give me an n of, okay, let me write this equation properly. So n equals to 1. So this is 1, 57.17 equals to 57.17 hertz. So we are looking for what n? For n, 57.17 that reaches 20,000 hertz. Okay, so how do I solve for n? 20,000 divided by 57.17 lah, obviously. So I get not a whole number, I got n is 349.8. Okay, so again, n must always be an integer. Kalau dia ada 0.8, maksudnya dia tak sampai lagi 350 harmonic, the 350th harmonic, which means that it only reaches 349 complete harmonic. So, our closed organ pipe, which is 3 meters long, has a frequency that overlaps with the audible range, 20 to 20 kilohertz, from n equals to 1 to n equals to 349 only. What is the value of 349 harmonic? 349 times 57.17 is equal to 19,952.23 hertz. Okay, so that is the maximum harmonic that overlaps with the audible range. Okay, I hope that makes sense. The point of this question was to emphasize that n is always an integer lah. Okay, so the rest is just using the right equation and finding out the harmonics of the closed organ pipe that overlaps with the certain frequency, with the audible range. Okay, now we move on to beats. Beats are alternations in loudness due to the interference of two waves of slightly different frequencies. Sekejap, tersilap ni. Of waves with different frequencies. Tadi, when we talked about the standing wave in string, in air column, we are assuming that the waves that overlap with each other has the same frequency. Sebab they are propagating and then they reflect. So when they reflect, they have the same frequency. So the overlap is between two waves of similar frequency. But beats happen when the two waves that overlap or superposition with each other do not have the same frequency, or their frequency is slightly off. Okay, as usual, let's talk about a scenario. So I have a tuning fork. I don't know why I have one, but I have one for this scenario. The tuning fork that I own is 243 Hz, right? So I don't know why I chose that frequency, but I have it. So I went to the shop and I asked the shopkeeper, hey, do you have a tuning fork that is also 243 Hz? And the shopkeeper said, yeah, we have a tuning fork that is 243 Hz. This is the one. So I bought this. So I bought a second tuning fork that has a similar frequency. So this is the bought one and this is mine. So this is new lah. This is old. Okay? So I know for sure that my tuning fork that I own is 243 Hz. So okay, I bought the new one and I took it home and I tried to play both of these tuning forks next to each other, right? So what do? I take a stick or whatever the thing is called to make it sound. I go ting for the first one, the one that I own. So I hear a sound. So I don't know what the frequency is because my ear is not robotic. I don't know how to calculate what the frequency is, but I know for a fact that it is 243 Hz based on the specification. And then while this guy is ringing, ting, like that, right? I also do it on the second tuning fork. So it goes ting as well. Now, if they both have the same frequency, I will hear something ting like that. Both of them resonate at the same frequency. But now I'm hearing ting, 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 ting. There is an alternation in loudness. That is the alternation in loudness. And when you hear ting, 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 it can be slow, it can be fast. Ting, 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 ting. When that happens, that is called a beat. So what is beat? What is a beat? It is when you have a frequency of a wave of two waves that have different frequencies and they overlap with each other. Which means that my conclusion is the shopkeeper lied to me, right? He told me it was 243, but it is not. Maybe it is 244. We don't know. So now I have a second tuning fork that I don't want and the frequency is 244 Hz. So the beat frequency between these two tuning fork is modulus of F2 minus F1. Doesn't matter if you subtract 244 with 243 or 243 with 244. The answer will always be positive. So the beat frequency between these two tuning fork is 1 Hz. Okay, so I can't trust that shop anymore. I have to go to another store. So that is beat. You have two waves of different frequency and they overlap. So the alternation in loudness is called the beat. Now let's take a look at an example because tadi tu saya guna mulut. Let's go to a more legit lah. Kejap, how do I share? Okay, so let's take a look. Kejap. So let's find out how a beat frequency sounds like. What happens when we have a lower beat? What happens when we have a higher beat? So this is the first example. We have 400 and 401. So the beat frequency is 1. So kita dengar sekejap. So the alternation in loudness is slow, right? It's like lembab lah. So what if I increase the difference between these two waves? So now our beat frequency is 10 beats per second, 10 Hz. First wave is 400, second wave is 410. Frequency beat is 10 Hz or 10 beats per second. So now it should be faster. Okay, so the alternation in loudness should not be, it's not supposed to be constant. Sebab the two waves have different frequency and the overlap where the constructive interference happen and where destructive interference happens does not have a pattern. So sekati dia lah, it's like random. So that was when you had a 10 beats per second. This is when you have 35. Your beat frequency is 35. So you can see the higher the beat, macam the higher the pitch, right? Macam pitch is not a formal term for this, but you can say like that. You can assume that when the beat is higher, what you hear is a higher pitch or a higher repetition rate. Okay? Okay, so that is beat frequency. And then, ni tak apa. Okay, so interference of sound waves when the path difference is an integer times lambda, you get constructive interference. Constructive interference, which means that you hear loud, the loudness. Okay, and then destructive interference is when you hear the silence. So the path difference is n plus 1 over 2 times lambda. Remember, n is always an integer. N always integer. So that is why when we have 1 over 2, this is when they overlap and the displacement becomes 0. You hear a moment of pause. N always integer. Alright. Last one, quality of sound, tuning fork. The tuning fork produces a single fundamental frequency. So this is how it looks like. Oh, tak ada. So tadi, this guy is flute, this guy is clarinet, this guy is tuning fork. So single at number 1. Okay, so musical instruments produces mixture of harmonics with the different intensities. But for the tuning fork, it only has one harmonic at the fundamental frequency, and that is it. However, for the flute, a note is a mixture of the first harmonic, the second harmonic punya intensity tinggi sikit, the third harmonic rendah sikit. So it's a mixture of harmonics of different intensities or different amplitudes. So you get a profile that looks like this. Okay, so that is for the flute. For a clarinet, it's much more complicated. The note consists of the first harmonic like this, and then the second harmonic is half of the first harmonic. The third is a little bit down, a little bit lower than the first harmonic, and so on. So they have their own profiles. So it is complicated, but they engineer it somehow. Okay, that's called music engineering. Okay. I think that's it for chapter 10. Do not forget to do your web assignment. It is due on Friday. Okay, so I'll see you later. Bye-bye.